Okay, it will be about logarithms and exponential functions. So let's first talk about exponential functions because they're like a simpler version. So what this is like you have like x to the power of y. And we kind of talked about in week 7, we talked about like exponents, rational exponents, and this is like kind of related. So it just brings back to exponent. So you have x to the power of y. And in this case, x and y can be like anything in the real numbers. So, we know that like a lot of functions have inverses. So for example, multiplication and division are inverses, and addition, subtraction. Or we can change this to y to the power of x because it would be like matching. So for example, in addition, you like x and y. So you have x and negative x. In multiplication, um x and 1 over x. And for example, exponents, you have like maybe x to the power of n and like the nth root, x to the power of 1 over n. And the thing about this is that these inverses like a lot of times you have inverses like you have it's like literally just like the inverse. Like the inverse function and the function are the exact same. But for example, in addition, um basically same thing, but backwards. And this is not the same for multiplication and exponents because, well, not every item has an inverse. For example, what if x is equal to 0? Then it wouldn't necessarily have an inverse. And over here, what if x is equal to like -1 and n is equal to like 2? Then, as we said before, it's not necessarily like an inverse because x squared and the square root of x, it's different because x squared, like x and the square root of x squared is different. And this kind of like tells us that inverse functions exist if we restrict the domain. So in this case, multiplication, you would be restricting the domain to x is non-zero, and for exponents, we restrict it to like maybe like n is an even like an odd integer and x is any number, or it's an even integer and x is any number. So yeah. So we have exponents, you have x to the power of n and you have x to the power of 1 over n. But this is just the inverse function for x, like y, right? If you like the base of the exponent. So what about like x? Then you would have the log function. So say that we have x to the power of y is equal to n, then we write log of x n is equal to y. So these two statements are equivalent. And yeah, so these two expressions are actually the exact same thing. Except the log function is unique because it has a different domain. Or not exactly, because you'll see that the variables will actually match up. So values that variables can be match up. So as an example, well, we know that n is like always greater than equal to 0, right? Whereas more specifically, it's greater than 0. And I think by convention, there are like some like domain restrictions that we just follow, even though technically some like work out. So yeah, I believe like n is like n is greater than 0. And you also have x is greater than 0. You have x is greater than 0. And you have like y can be anything, I think. So it's in real. Yeah, so you can kind of like deduce this all from like going backwards to x to have y equals n because we're more familiar with that. So like as practice, like just to get used to like the notation, have like log of like 381. And we can like think about that for a second. Okay, so this would just be 4 because we know that 3 to the power 4 is equal to 81. And maybe we can try like log of like 5, 1, 2, 5. So this is just 5. This is just 3 because 5 to the power 3 is equal to 1, 2, 5. Okay, so I guess we can move on to like some properties of logs. So we have log, okay, right. By the way, if you have like um wait, I guess we should go over this. So and by note like by notation or by convention, log 10 of like n is just equal to log n. So you can just omit the 10. And then we have another thing called the natural log function. So this is just ln x, which is basically ln or like log of base ex. And this value e is about 2.718. And I think like yeah, it's like a really important number and appears in like many different math problems and just like concepts in general. So yeah, these are two things to know. So I guess we can move on. So like some log properties. So the first one is Addition. So this basically says that if you have log of x is equal to log of y, or like wait, um okay, in this part we're just going to like not care about the base. Or like I guess we should wait here. Log a base b plus log a c. This is just log a b times c. And we can prove it here. So like let's say log a b is equal to n and log a c is equal to m. Then we have a to the power of n is equal to b, and then a to the power of m is equal to c. And then we can multiply these two together, and we have a to the power of n times a to the power of m is equal to b times c. And we know that by exponent rules, you can add the two exponents and an m here because they have the same base. And now we can write, this is the definition of log. B times c is equal to m plus n. And then we substitute back what m and n are, and we have log ab times c is equal to log ab plus log ac. So yeah, as you can see, like we're basically just taking the definition of a log and then like using exponent rules to get the final formula we have. And since addition allows us, we also have subtraction. And then we have distribution, which says that log a to the power b to the power c is equal to c times log ab. And I guess we can try proving this ourselves first. So, because like, okay, using the ideas of addition, maybe we can try proving distribution as well. It's like pretty similar. So maybe we can think about that. Alright, I guess we can try to prove this now. So we kind of just like do the same thing. So let's say like log let's substitute like one of them first. So let's say like log AB is equal to like n. Then this tells us that a to the power of n is equal to b. And then we can think about like c log AB, and then this is equal to cn, right? So by substitution, you have a to the power of cn is equal to b. And then this means that a to the power of n to the power of c is equal to b to the power of c. So a to the power of cn is equal to b to the power of c. And this means that log this means that log a, yeah, wait, maybe I should write this in another way. So okay, sorry about that. So let's we can raise all of this to the power of c. So log a to the power of n power of c is equal to log b to the power of c. And by exponent rules, we have a to the power of n times c is equal to b to the power of c. And then you take the log to get a to the power of b to the power of c is equal to n times c. And when you substitute what n is, you get log a b to the power of c is equal to log ab times c. So yeah, that's for distribution. And overall, I hope you guys like get the gist already that like a lot of it is just manipulating exponent laws. Okay, so here's another one. So we have log a b over wait, yeah, is equal to log cb over log log ca over log cb. And c can be anything as long as the like it follows the domain restrictions, and as you can see this is called base change because we're changing like the base here from a to c. Wait, it should be b. Okay, so I guess we can go over that like after I try it for a bit. Okay, so we can just like basically use the same rule. So let's write log C of B is equal to n, and log C of A is equal to n. So by using the definition of a log, we get C to the power of n is equal to B, and C to the power of m is equal to A. And then we can basically just say like, we can like basically take like the log of it, like if we substitute, so this is just saying like, if we take a look at the left hand side, we have log A, B is equal to log C to the power of n, C to the power of n. And you can think about like the number of times like it goes inside, if that makes sense. So like and like you can see like how if you substitute it, this like overall like you can see how like it cancels out, right? Okay, and then the next one is I guess we can like be more concrete with this. So like wait, so first we substitute like first we write it as like the definition, and then you take the log b of both sides. Or you take the log c of both sides. Or if you like multiply it, then it like it works out. Okay, so the next one is the yeah, it's basically saying that log a to like a to the power of log ax is equal to x. So hopefully this like kind of intuitively makes sense. So if we like look at these two, like this is like log ax and this is like a to the power of y, I guess, right? So like what we're doing right now is like you're taking like a number x. If you write like x is equal to y to the power of a, if you write x to the power x is equal to y to the power of a, then you get a is to the power of y, right? Or like wait, shoot, there should be a to the power of y. So then you get a to the power of log ax is equal to a to the power of um y by definition. And it's like you can see how like it cancels out. Because like we said earlier that exponents and logs are like kind of like inverse functions. Okay, so now some other stuff like just like um basic log like calculations. So log anything of 1 is equal to 0, and yeah, that's pretty important because we know that like anything to the power of 0 is equal to 1. Okay, and then yeah, so now we can do some like solving problems. So like maybe we can say like example. So 3 to the power of like solve for 3 to the power of 3x plus 1 is equal to 3 to the power of 2 x plus 5. So we can think about that. Okay, so one way you can do it is like you can just take the log of both sides. We're allowed to do this, so it's like kind of the same as taking the exponent of both sides, but you're doing it inverse. So 3x plus 1 is equal to 2x plus 5, and we get x is equal to 4, right? And then make sure like we plug this back in, so we have like 3 to the power of 13 is equal to 3 to the power of 13, which is right. So I guess the general idea is that like if base is the same, then you can just directly go look at the exponents. Which is basically what we did from this step to this step when we were taking the log. Okay, so I guess here's like a similar problem. You're like, here, it is this. Okay, so this is like kind of the same thing, except we have to use the exponent rules. So we know that 4 is equal to 2 to the power of 2, and 8 is equal to 2 to the power of 3. So by substitution, you have 2 to the power of 2 times 5x plus 1, and 7 is equal to 2 to the power of 3 to the power of 3x plus 1. And then we know from earlier that we can like, wait, kind of like as an exponent law, you multiply the exponents. So this is 2 times 5x plus 7 is equal to 2 to the power of 3 times 3x plus 1. And then since the base is the same, you can just look at the exponents. And then you get 10x plus 14 is equal to 9x plus 3. And then you kind of like subtract and you get x is equal to negative 11. And when you plug it back in, it should be the right answer. Okay, so guess now we can talk about like, let's do like something with log properties. Okay, so for this, we kind of just like employ our log properties. So you know that when you subtract two logs, you just like get them divided over each other. So we write this as x log x minus 3 over x minus 1 is equal to 5. And I guess like by convention, log of something is just log 10 of that. So we have a 10 here. So if you write it, then it's x minus 3 over x minus 1 is equal to 10 to the power of 5. And then now we can kind of just like solve it. It might look a little messy, so it would be x minus 3 is equal to 10 to the power of 5, x minus 10 to the power of 5. And this gives us x is equal to 10 to the power of 5 minus 3 over 10 to the power of 5 minus 1. So yeah, okay, I guess we can just like keep solving problems. So, another problem is if you have like, okay, ln x plus ln x minus 2 is equal to 5. I guess, I think it's ln 15. Yeah, okay. Maybe you guys have time to do that. Okay, so for this, we just use our log properties again. So this is ln x times x minus 2 is equal to ln 15. And we can kind of like raise everything to the power of e. So this gives ln x minus 2 is equal to e to the power of ln 15. We know that by doing this, we can cancel like the base out. So now we can just have x minus 2 is equal to 15. And then we expand this to get x minus 2x is equal to 15. And then we have x squared minus 2x minus 15 is equal to 0. So by factoring, you get x minus 5 times x minus plus 3 is equal to 0. So x is equal to 5 or negative 3. And now we will like kind of think about what happens when we plug this in. So when we plug in like 5, it's okay, ln of 5 times 3, or that's just ln of 15, which is fine. And we have ln of x negative 3 and x minus 2. So this is negative 5 times negative 3, which is 15, which is good. Okay. And as a side note, it's not always true that you can kind of like apply some of the log properties. Like, for example, it's not always true that you can like go from here to here, because by doing so, you kind of change the domain of the function, right? So like x and x minus 2 has to be greater than 0, but once you like combine, like once you separate them or like you combine them, you have ln of like x has to be greater than 0 and x minus 2 has to be greater than 0. And yeah. So I guess similarly here, if you have negative 3, you substitute it in and it actually doesn't work. So that's why you have to like kind of be careful when you're using these formulas. Okay, so I guess our last example is a little bit complicated, or not really, but it's like the solution is kind of hard to think of. So it's 5 to the power of 2x plus 1 is equal to 7 to the power of x minus 2. Okay, so we can just go over this real quick. So the thing about this problem is that you have to take the log, but it low-key doesn't matter which like base you take. So like I guess I can just take the like log e because it's nice. So we take the ln e of both sides to get ln 5 to the power of 2x plus 1 is equal to ln 7 to the power of 2x plus 1, or x minus 2. And then we can use the log properties to get this. So it's equal to x minus 2 ln 7. And then we can kind of expand this to get 2 ln 5x plus ln 5 is equal to ln 7x minus 2 ln 7. And then we can like just like rearrange it to get 2 ln 5 minus ln 7 times x is equal to negative ln 5 minus negative 2 ln 7. And then when we divide, we just get x is equal to ln 5 plus 2 ln 7 over 2 ln 5 minus ln 7. I guess we can simplify this and it would be like, it'd be something like ln, like 49 times 5, so that's 245 over ln, and that's like 25 over 7. And we can use like the change of base formula, so it's like log 25 over 7 and then 245. And this is like kind of annoying, like the overall expression. But it's true that like doesn't matter what base we take. You can try with like any number and we'll see that like it doesn't matter because we're just trying to use the property. And ultimately E doesn't really appear anyway either, so that kind of like shows. Okay, so yeah. Thanks for coming and see you guys next week.